Hi, welcome to Chapter 8. In the past chapter, we took a look at RL circuits and RC circuits, and we labeled those first order systems. In this chapter, we will take resistors, inductors, and capacitors into one single circuit. And combining resistors, inductors, and capacitors, we then get an RLC circuit. And by getting an RLC circuit, we now have a second order system. So in this chapter, we will go over second order systems. We will cover both RLC circuits in parallel and RLC circuits in series. So up until this point, we've taken RL circuits and we've had RC circuits. And both of these are first order circuits, meaning they have things like dV dt, and this means and di dt. This is a first order circuit. Now we will combine the resistors and the inductors and the capacitors together. And by combining those, we get an RLC circuit. And an RLC circuit is a second order circuit. So it's a little more advanced. And in second order circuits, we have things like the second derivative of voltage and the second derivative of current with respect to time. So in these circuits, we need to consider time. Okay, we need to consider time. Let's consider a capacitor. Let's take a look at a capacitor. So for a capacitor, remember we wrote it like this. And let's say we have current going this way, and we write our sign convention in the passive sign convention. Passive, going from plus to minus here. And we have the voltage across the capacitor. Let's call that VC, and we'll call this IC for capacitor. Now, if we take a look at the capacitor, remember when we had a switch, when we turn it on or turn it off, we would examine things time before 0 and time greater than 0. So if we graph this, let's graph this. Okay, and this is time. This is time in seconds. And this can be our voltage across the capacitor. This is the voltage here. Now, this point here is t equal to 0. And if we graph this, it may look something like this. We may get a straight line here, and it comes down like this after after we turn it on. The one thing we need to have is the voltage at 0 minus, meaning on this side over here, must equal the voltage at 0 on the plus side. So this means the voltage is continuous. The voltage is continuous. And if we take a look at another example, I'm going to draw the same thing. We have T and the voltage across the capacitor. And let's, for example, we have this and this. This cannot happen because these are not continuous. This is not true. So this cannot happen. So it must be continuous across the capacitor. The voltage across the capacitor must be continuous. Now let's look at the inductor. And we can draw an inductor like this. This is our inductor. And we use the passive sign convention. So if the current across the inductor is this way, and then we can call this the voltage across the inductor here. Now with inductors, we have the situation where the current at right before 0, right on the left-hand side, is equal to the current on the right-hand side of 0. So when we switch things on or switch things off, when the circuit changes, the current must be continuous. It must be continuous. So if we were to graph this, and we were looking at the current across the inductor, I, and this was T, we may have something that looks like this maybe. We have something like that. That is continuous. What we cannot have, I'll draw it here. The current across this inductor cannot be something like this. This cannot happen because it must fulfill this requirement here that the current is continuous. So to summarize, for a capacitor, voltage cannot change abruptly, meaning quickly, abruptly, meaning quick, fast. And for an inductor, the current cannot change abruptly. So this term here, abruptly, meaning fast or quick. So it cannot change abruptly. It must be continuous. Let's review a few things. So we have, for example, a voltage source with a resistor and a capacitor. And let's say we have a switch here, a switch, and at t equals 0, this closes. Okay. Now at time equals infinity, at a very long time in the future, after a long time, we would have a circuit like this. Okay. Because the charges build up on the plates. They build up on the plates there. So remember that the current across a capacitor is equal to C dV dt. And after a long time, this is 0. So the current at time infinity is 0. So it behaves like an open circuit. It behaves like an open circuit. Now let's take a look at the inductor. Get another page. So for the inductor, let's say we have a voltage source with a resistor and then the inductor here. And then we'll put a switch here. And this will close at time equals 0. Okay, we have a voltage source, and we have a resistor and our inductor. At time equals infinity, here, at time equals infinity, what we have is this inductor will act like a short circuit. So the circuit will look like this. Because the voltage across the inductor, is equal to 0. Because we have the equation, the voltage across the inductor is equal to L di dt. Now, if the voltage or the current is 0 at time infinity, then the voltage across the inductor is 0. So in a short circuit, there is no voltage drop across the inductor here. So just remember these two things. After a long time, the current across a capacitor is 0. And after a long time, the voltage across an inductor is 0. Okay, so let's do an example. So we have a voltage source here, and this voltage source is connected to a resistor, which is then connected to an inductor, and then we have a resistor here that is connected to a switch that opens at t equals to 0. That opens at t equals to 0. And then that is in parallel with a capacitor. Now this capacitor here is 0.1 farads, and we have a voltage across that capacitor. And this is 2 ohms. This is 0.25 Henry. And this resistor here is 4 ohms, and then our voltage source is 12 volts. So what we want to find is, this is I. We want to find this current at time 0 plus right after this switch opens. Right immediately after this switch opens. So we want to find the current. And then we also want to find the voltage at 0 plus. That is the voltage across here right after this switch opens. Immediately after. Part B, we want to find di dt at 0 plus. Right after the switch opens, we want to find the derivative of the current with respect to time. And also, we want to find the voltage at 0 plus, the derivative of that with respect to time. And then lastly, we want to find the current at infinite time and then the voltage at time infinity as well. So we're going to look at 3 different scenarios with time. We're going to look at T0 minus, and then we're going to look at T0 plus, and then T infinity. We're going to solve this 3 ways, 1, 2, and 3. Okay, so let's draw a circuit for each one of these. At T 0 minus, this switch is closed here. We have this closed. So all of the current is coming down here. In addition, this here is acting like a short circuit. So what we have 12 volts. And then we have our resistor, and then our inductor is a short circuit, and then all of our current is coming down this way. So we have I here, we have I. This is 4 ohms and 2 ohms, 4 ohms, 2 ohms. Okay, so this is step 1 for here. And the voltage, this V here, is actually this voltage across here. That's the voltage from here to here, because those must be the same here. So we can draw, if we want, we can draw this like this. Okay, we're looking for the voltage there. So let's solve part A here. Part A. Well, at I at 0 minus is equal to 12 volts divided by, these two are in series. These two are in series. So that is 4 plus 2. Which is 6, and this comes out to 2 amps. But we want to find this. Remember, we know that I 0 minus must equal I 0 plus for an inductor. So we have 2 amps here. So that is one solution. The next thing we want to find is the voltage. Voltage at 0 minus, we can do voltage divider, is 2 divided by 4 plus 2 times this 12 volts. And that is 2 over 6, which is 1/3, and then that comes out to be 4 volts. 4 volts. And we know the voltage across a capacitor cannot change abruptly. So we know that this is 4 volts because this is across a capacitor. This is a capacitor here. Okay, so that is our part A that we have done. Now let's work on part B, and we'll draw circuit number 2. Circuit number 2 is at T 0 plus. And this circuit, we have our resistor. Let's draw our voltage source. And we have here, we have this is an open circuit now. And then oh, I forgot my inductor. And then this is an open circuit now. And we have our capacitor over here, which is, what is that value? 0.1 farad. And then this is 0.25 Henry. And this is 4 ohms. And this is I. And then this is our voltage V. Okay. So by doing this, we've already said that I0 negative is equal to I0 plus, which equals 2 amps. So that is the current across here and the current here as well, because these are in series now. These are in series. So with that, we know the current across the capacitor. So the current here is 2 amps, and we know the current across a capacitor is equal to C dV dt. Okay. C dV dt. And if we know the current, we have the current is 2 amps, and we have the capacitor, which is 0.1 here, we can figure out dV dt. And dV 0 plus t dt is then equal to 2 divided by 0.1, which is 20 volts per second. So that is our answer for that. Now let's look at I. Now let's take a look at the, we'll try to find the current, the di 0 plus dt here. That's what we're looking to find. And if you remember that the voltage across an inductor is equal to L di dt. We can say 0 plus here. Okay. So let's do a KVL around the outside. The KVL down around the outside. So we'll start here, and that is negative 12. We're doing KVL. Negative 12 plus 4 times the current through here, and the current is I0 plus right now. That's the current through here. And then we're going to call the voltage across here, let's call that VL. The voltage across there is VL. So we'll say plus VL 0 plus, that's the voltage across here at 0 plus. And then we have our voltage across the resistor, which is plus V 0 plus. is equal to 0. Now, we know that this current here is 2, and we know that this here, we know this voltage from part A, and that voltage is, what's that, 4 volts? 4 volts. So we have negative 12 plus 8 plus VL 0 plus 4 volts equals 0. Plus 4 equals 0. And so that comes out VL plus 0 plus is 0. 0 here. And that means that if we want to figure out this now, we have VL 0 plus is equal to L dI 0 plus divided by dt. The left-hand side is 0, and L is 0.25 Henry. And then we have dI 0 plus dt, which we're going to see that that is equal to 0. So dI 0 plus dt is equal to 0. So that is the second part, analyzing the circuit at t 0 plus. Now we will take a look at analyzing our third step when t is equal to infinity. So when t is equal to infinity, we still have our voltage source, which is 2 volts. We're going to have our resistor. And we know that the inductor is going to behave like a short circuit. Okay? And the capacitor is also, it's behaving like an open circuit here. So we have our 4 ohms. This is our voltage across our inductor, L. So we can say VL. And this is our voltage V here. Now, if we want the current and the voltage, I think you can see at I infinity, there is no current. This is an open circuit. There is no current. So that is going to be equal to 0. And likewise, the voltage at time equals infinity. Since it's an open circuit, there is no current, so this voltage here is going to be equal to this voltage. So that is 12 volts here. And that is our last part of our solution, analyzing the circuit at t equals infinity. We will now examine a special circuit called the source-free Series RLC Circuit. So source-free means no independent source. So we do not have a voltage source, and we do not have a current source, right? So no, that means source-free, no sources. And series, you know what series means. And we have R, meaning resistor, L, meaning inductor, C, meaning capacitor circuit. So the circuit looks something like this. We have a resistor, an inductor, and those are all in series, and we have a capacitor over here. So the capacitor has a value of C, and we initially store a voltage in the capacitor. So initially the voltage, the capacitor has energy. The capacitor has energy, and we have our inductor, and this initially has a current here. And then we have the resistance here. And we'll take a look at the current in this loop here. So with this circuit, we can do several different things. So let's do KVL on this circuit. So KVL, we have the current times the resistance, right? So we have a resistance here, so it's R times I here. And then the voltage across the inductor here. Remember, the voltage across the inductor is equal to L di dt. And lastly, the voltage across the capacitor, here is plus 1 over C, and then we integrate from negative infinity to t, I of t dt. So I of t dt. And that is equal to 0. So these are all of our components. This is the resistor, this is the inductor, and lastly, this is the capacitor. So let's examine at t equals 0. At t equals 0. At t equals 0, we have the voltage across the capacitor here, right? The voltage at time 0 is equal to 1 over C, the integral from negative infinity to 0, I dt. And we know initially it has a charge, which is V naught. Initially it has that. And then also we know that the current at time 0, is equal to the initial current across the inductor, I0. So knowing these two things, we can do KVL, we can sub into KVL at time 0. So KVL, KVL here at time 0. Time at t equals 0. So if we do this, we get this equation. We have R times I at 0 plus L times di at time 0 dt. And then plus, we have this mess here, but at time 0, we know that that value is just V naught is equal to 0. So we know that this must be true. This equation must be true for our source-free series RLC circuit. That must be true. So what we did there is took equation 1 and we just subbed in that to equation 1. And we got this equation. Now, additionally, let's take equation 1 again. I'm just going to rewrite equation 1 here. We have Ri times, or plus L di dt plus 1 over C integral from negative infinity to t, I of t dt equals 0. Now we have this is the same equation. This is equation 1. We're going to differentiate this. We're going to differentiate this with respect to t. With respect to t. So what we get is R di dt plus L d squared I dt squared. And this, we just get I over C equals 0. Now that we have this equation here, we did this by differentiating this equation. So we took this equation here and differentiated this with respect to time, and that is equal to this. That is equal to this equation. And we can now rearrange this equation. So I'm going to divide everything by L. Divide by L. So we have R over L di dt plus d squared I dt squared plus I divided by LC equals 0. Now rearranging this equation, R over L okay. So this equation here, because it has this, the second derivative here, this is what we call a second order equation. Second order equation. And we can't use traditional methods to solve this. We need to take a glimpse into this equation to be able to solve it multiple ways. So we must look at the solution, and the solution to this equation, the solution is going to take a general form. General form. And so this is what it's going to look like. So it's kind of going to look like this. So what we have here is I is going to look something like A to the E times S times T. So the solution to this equation looks something like this. And we're going to investigate, we're going to look into this equation more. So how do we solve these equations? How to solve source-free series RLC circuit. All right. So we have our circuit. And we have our resistance, we have our inductance, our capacitance. We know that this is an initial voltage of V naught, and then we have our initial current here, which is I naught. So how do we solve this? Well, step one, we need to calculate alpha and omega naught. So alpha and omega naught. Okay. So we have alpha and omega naught. And how do we calculate those? Well, alpha is equal to R over 2L. And omega naught is equal to 1 divided by the square root of L times C. And this here is what we call the resonant frequency. Resonant frequency. Resonant frequency omega. So once we have those calculated, we then check the equation. We check alpha versus omega naught. So we compare these two. We compare them. So if alpha is greater than omega naught, then we call this, it is overdamped. We call it overdamped. Overdamped. If alpha is equal to omega naught, the resonant frequency, then we call this critically damped. Critically damped. Critically damped. And lastly, if alpha is less than omega naught, then we say that this is under damped. So we take a look at these words over and under. Over means going over, under, go under, over, under. You would, if you had a bridge with water, and this was you, this is going over the bridge, and then this would be going under the bridge. So over and under. So we have overdamped and underdamped. And then right in the middle, we have critically damped. So what we're trying to do is solve this equation for the current. So if trying to solve this equation for the current, we must check these three things first. So let's move on. Let me get another sheet here. So if alpha is greater than the resonant frequency, this is the overdamped case, overdamped. Then our equation comes out to look like this. Our equation is I of t is equal to A1 e to the S1 times t plus A2 times e to the S2 times t. So this is how our equation, this is our solution to our equation. And let me tell you what S1 and S2 is. S1 is equal to negative alpha plus the square root of alpha squared minus omega naught squared. Okay, and then S2 is equal to negative alpha minus square root of alpha squared minus omega naught squared. So these two go into the equation here and here. And then we would plug those in, and then we would solve for A1 and A2 based on our initial conditions of our circuit. So this is the equation for the overdamped. So that you can think of that as the first equation. Now, if we have alpha equal to omega naught. This is the critically damped. And what we say in this equation, we have the solution here looks like this. All right, I of t is equal to A2 plus A1 times t times e to the negative alpha times t. So this term here is our critically damped equation. So we have equation 1 if it's overdamped. This is equation 2 if we have critically damped. And lastly, we will go to the underdamped case. So if alpha here is less than omega naught, we say underdamped. Underdamped. And this is probably the longest equation. We get I of t is equal here to e to the negative alpha times t times b1 cosine omega d times t plus b2 sine omega d times t. And here, omega d, and here, we have an equation for that. So omega d, the damped frequency, the D means damped frequency, is then we have the square root of omega naught squared minus alpha squared. Okay, so this we plug into here and here, and we already have alpha, and we would solve for B1 and B2 through the initial conditions of the problem. So with these second order systems, we must first, step 1, calculate alpha and omega naught. Step 2, we then plug in the appropriate equation. And now let's move to step 3. In the last step, after we have the equations, we must sub in for these variables here and here. And we can do that if we know things like I of 0 is equal to a certain value. We can plug that into these equations and we can solve for A1 and A2, right? So we use the initial conditions to be able to solve these equations. So let's do an example problem where we have a circuit which has a voltage source and it has a resistor and it has a switch. That's resistor. And then it has a switch, and that is connected to a capacitor, resistor, and then here we have a resistor, and then we have an inductor. Okay, so this is 10 volts, this is 4 ohms, and this opens up at t equals 0. And here we have 0.02 farad, and this is 3 ohms, and this is 0.5 Henry, and this is 6 ohms. And we have a voltage across here, V, and we'll call this I here. Now, what we want to find is I of t, this current here. That's what we're trying to find. So what we we're gonna assume that it is in steady state before t equals 0. So it's in steady state, it's not changing. It's not changing. So let's first analyze this circuit for time is less than 0. So this is all connected. Now, if we do that, we have our voltage source, which is 10 volts, connected to a resistor, and this is connected here. So that is here. This capacitor acts like an open circuit. It is all charged up. So no current is going down here. So we have a resistor, and this inductor is going to act like a short circuit. A short circuit. So we have something like this. And this is I, and this is 6 ohms, this is 4 ohms. And the voltage across this resistor is V. So it's the same here, right? The voltage across this, because there's no current here, the voltage across this here is equal to the voltage across this resistor. That's V. Okay, so if we analyze this circuit, I at time 0 minus is equal to this voltage, 10 volts, divided by the resistance, which is 6 plus 4 ohms. 6 plus 4 ohms. So that is 10 divided by 10, which is 1 amp. And since we know that there's an inductor right here, we know that that is also equal to I0 plus. We have that. The voltage here, the voltage at 0 minus is equal to 6 divided by 6 plus 4 times 10, which is 6 volts. Is that 6 volts there? All right. So that is 6 volts. And we also know that this voltage will be the same because it's a capacitor, the voltage at 0 plus. Right? So we know those two. Now let's take a look and analyze this circuit for t is greater than 0. So when t is greater than 0, this is opened up. So no current is flowing here, across here, no current. So we only have this side over here. So that looks like this. So we have a capacitor, a resistor, then we have a resistor, and then an inductor. And this is 6 ohms, 0.5 Henry. 6 ohms, 0.5 Henry. This over here is 3 ohms, and then 0.02 farad here. And this is our voltage, and we have I here. Now we have this circuit, and we need to analyze this circuit. And this becomes a source-free series RLC circuit. So there's no source. We have everything is in series. And we can combine these two resistors because they're in series, so that's 9 ohms. And so to do this, to start this problem, remember we need to figure out alpha, and alpha is equal to R over 2L, which is equal to our total resistance, which is 9 ohms, divided by our 2 times L, 2 times 0.5. So that comes out to be 9. 9 here. And then we also need the resonant frequency, omega naught, which is equal to 1 divided by the square root of L times C. And that is equal to 1 divided by the square root of 0.5 times our 0.02. And that value comes out to be 10. So now we compare these two values. And we see that alpha is less than omega naught. That is 9 is less than 10. So because of this, we have an underdamped scenario. It's underdamped. So let's keep working on this. So the solution for an underdamped, let's take a look here. We have it underdamped. All right, underdamped. And the solution for the underdamped scenario looks like this. I of t is equal to e to the negative alpha times t. And then we have b1 cosine omega d times t plus b2 sine omega d times t. This is our solution here. Now we've already figured out alpha, which we said was 9. And omega d, this is the damped frequency. The d means damped. So this is the damped frequency. That is equal to the square root of omega naught squared divided by alpha squared, or minus alpha squared. So that comes out to be the square root of 10 squared minus 9 squared, which then is the square root of 19, which is 4.359. So here we place in our values. We have e to the negative 9t times b1 cosine omega d is 4.359 times t plus b2 sine 4.359 t. All right, so we don't know what b1 and b2 is yet, so we need to solve for b1 and b2. We do know that I of 0, remember from the very beginning of the problem, is 1 amp. So if we put 0 into this equation, that's e to the 0 times b1 cosine of 0 plus b2 sine of 0. Sine of 0 is 0, and cosine of 0 is 1. So we have 1, and this is 1. So we have 1 equals b1. So we know b1 is equal to 1. So we know this value. Now we need to figure out b2. What is b2? So let's take a look at our circuit again. And we have our capacitor, and that's connected here, and then we have our inductor, which is then connected to another resistor. So if we take a look at the circuit, and we have I, and this is 6 ohms, and this is 3 ohms, and this is 0.5 Henry. All right. We know that the voltage at 0, this voltage across here, is equal to what? To 6 volts. To 6 volts. We found that earlier. So we can do our equation across here. We can do our KCL, or our KVL. We can do our KVL. So our KVL, if we want to start here and go across this resistor, we have 3 times I, and then across this this capacitor, we know the voltage here. So this is 3 times I0. And we know the voltage across this capacitor here is 6, and we're going negative to positive here. So that's -6. And then we have this 6 ohm resistor, which is 6 times I of 0. And then lastly, we have this inductor here. And we know the voltage across that inductor is equal to plus L di dt. And L here is 0.5. So let's just put in 0.5. Just put in 0.5. And this is I of 0 here. And set that equal to 0. Okay, we can combine these two terms. We can combine this term. And we can combine this term. And that is equal to 9I0 minus 6 plus 0.5 di dt 0. Now we can move this to the other side. We can move this to the other side. So simplifying this equation here, we have di 0 dt is equal to 12 minus 18 times I of 0. All right, so that's 0.5 multiply here. And we know that this is 1. We know that this value here is 1. So we have our di at 0 dt is equal to -6 volts per second. Or, no, I'm sorry, amps per second. Amps per second here. Now we're going to use this. We're going to use this here. And how we're going to use that is we're going to take this equation here. We're going to take this equation. Let's take a look. And then we're going to take the derivative of this equation. So we're going to take di dt. We're going to take the derivative of that. So to do that, we can take the derivative by taking the derivative of the first, -9 e to the -9t, times the second. Plus the first times the derivative of the second. Let's just put this down here. Let's just put this down here. And we'll have e to the -9t there. And take the derivative of this, where we have 4.359 B1. Cosine is sine here. Let's make sure I did that right. Cosine is negative sign. So we need a negative out here. Negative sine of 4.359 t plus B2, or 4.359 B2 cosine of 4.359 t. So we have both of those. That looks right. And we now put in 0 here. So this goes to 0, and this goes to 0, and this goes to 0. 0 here, and 0 here. So this term here is 1. So we have what this comes out to be is equal to negative 9 B1, or parentheses, B1, that is 0 here, plus, this is 1, and here we have, this comes out to 0, this value is 0, sine of 0 is 0, plus 4.359 B2, this term here. And we already know that this is equal to negative 6. So we put in negative 6 here. And solving this, we know B1 already. B1 is 1. So that is negative 6 plus 9 divided by 4.359. Okay. So that means B2. That means B2 comes out to be 0.6882. Okay, so now we have solved, we have B1, and now we have B2 here. So we can write the total equation for the current. The total equation of the current here is I of t equals e to the negative 9t times cosine 4.359 t plus 0.6882 cosine of 4.359 t. So that is the total equation here for this problem. That is the current. We will now examine a new circuit called the source-free parallel source-free parallel RLC circuit. So the source-free parallel RLC circuit. So what we have here is a circuit that looks like this. We have a resistor, we have an inductor, and we have a capacitor. Here, here, and here. And the capacitor we C, and then we have L, and then we have the resistor. And we call this the voltage V up here. So these are all in parallel. These are all in parallel. We can put our ground down here. And the initially at the start, we have the voltage across the capacitor is V naught, and we have initially the current across the inductor is I naught here. So at I of time 0, we have this is equal to I naught. And remember that the current across a inductor can be found by integrating from negative infinity to 0 v of t dt. So we're integrating, and I forgot the 1 over L. So let's write that again. Oh, let's write that again. So it is 1 over L integration, negative infinity to 0, v of t dt. Okay, and we also know that the voltage across the capacitor at time 0 is V naught. So we know these two things. Okay. So if we do KCL, we're going to do KCL up here, KCL, and we can write our, our currents here, here, and here. So we have in minus out. So we will have our current here is going to be equal to V divided by R, and that is out, so that's going to be negative. This one is out, and here we have our negative 1 over L times the integration of negative infinity to t vt dt. So the integration of that is the current here. And then we have our current across the capacitor. The current across the capacitor, remember, is C dV dt. And that is all equal to 0. Now we can take that and multiply the whole equation by -1, and we can then write these as positive values. These are positive. So this is our equation for KCL here. Now, by doing this, we can differentiate this equation with respect to t. So we're going to take the differential here, d dt here. So by doing that, we get dv dt times 1 over r right here. And then here we get 1 over L, and the derivative of this is just V, and then we have plus C d squared V over dt squared equals 0. So rearranging this equation, we'll rearrange this equation. So we'll divide everything by C, so we get 1 over RC dV dt plus 1 over LC V plus d squared V over dt squared, and that is equal to 0. And lastly, let's just rearrange this. We get d squared V dt plus 1 over RC dV dt plus 1 over LC V equals 0. Now let's not forget this squared term here. So that's squared. Now this is a second order differential equation. Differential equation. This is this here. So to be able to solve this, this will have multiple solutions. So to be able to solve this, we need a few values. We first need to calculate, step 1, calculate alpha. And alpha is equal to 1 over 2 RC. And then we need the resonant frequency of this circuit, which is equal to 1 over the square root of LC. This is the same that it was for the source-free series RLC circuit. And so we compute those, and then we need to secondly determine what type of circuit it is. So we have, if alpha is greater than omega naught, then we have an overdamped case. Overdamped. So the solution for the voltage V of t is equal to A1 e to the S1 times t plus A2 e to the S2 times t. So what are S1 and S2? Well, S1, S2 are equal to S1 comma S2 are equal to negative alpha plus or minus the square root of alpha squared minus omega naught squared. So there we would plug in, so this is plus, this is minus, and we would plug those in. And then this is the equation for our voltage. Now we would need to use our initial conditions to solve for A1 and A2. Okay, so it's overdamped. If alpha is equal to omega naught, it is critically damped. Critically damped. And for the critically damped case, we get the voltage time t is equal to A1 plus A2t times e to the negative alpha times t. All right, so this is first one. This is critically damped. And then the last one we have, if alpha is less than omega naught. We call this underdamped. Underdamped. And here the equation's a little bit longer. We have V of t is equal to e to the negative alpha t and A1 cosine omega d, this is the damped frequency, times t plus A2 times sine omega d times t. So this is the condition, and here we have omega d is equal to the square root of omega naught squared minus alpha squared. So with these three conditions, we have our three equations. We have our three equations here. This is our first equation, our second equation, and then lastly, our third equation. And then in step three, we needed to figure out, find A1 and A2 based on our initial conditions. So based on our initial conditions. So for example, if we go back to our circuit here, right, we know that the voltage at 0 is V0. So that is one of the initial conditions that we can put down. So if we know that V0 is equal to this initial voltage, that will help us solve for A1 and A2. Additionally, if we know the derivative of the voltage at time 0, we can take the derivative of these equations and set them equal to the known value to help figure out A1 and A2. So to figure out A1 and A2, we need two equations. So usually we use this and we use the derivative to be able to figure this out. So let's do an example problem. And I'm going to draw our source-free RLC circuit that is in parallel. We have L, R, and C. And this is our voltage up here. And we have our ground here. And then we're going to have our current through each of these here. And we have our initial voltage. Our initial voltage here is V0. That is our initial voltage with our initial current here. Now with that, we have our circuit. And what we want to do is we have our voltage at time 0 is equal to 5 volts. And our current at time 0 here is 0 volts, or 0 amps. L is equal to 1 Henry. So this is equal to 1 Henry. And our capacitance is 10 millifarads. 10 millifarads for our capacitance here. And our resistor is equal to 1.923 ohms. Okay, so here are our values. Now we want to solve this circuit. So remember, the first step is to figure out alpha, and alpha is equal to 1 over 2 R times C, which is equal to 1 divided by 2 times 1.923, this value here, 923, times our capacitance, which is 10 times 10 to the negative third, because it's milli. So this value comes out to be 26. And next we need to calculate our resonant frequency, which is equal to 1 divided by the square root of L over C. So, excuse me. That is 1 divided by the square root of L, which is 1, times 10 times 10 to the negative third for the millifarads. And that is equal to 10. So we have the case where alpha is bigger than omega naught. And if you remember what we call this case, we call this case the overdamped case. This is overdamped. So we have the equation V of t is equal to A1 E S1 times t plus A2 times E S2 times t. So this is our equation. And with that equation, we know that this is the equation, and S1 comma S2 is equal to negative alpha plus or minus the square root of alpha squared minus omega squared. So this is equal to negative alpha, which is negative 26, plus or minus the square root of 26 squared minus 10 squared. And what this comes out to be is S1 is equal to negative 2, and S2 is equal to negative 50. So we have this. Next, let's plug that into our equation. So V of t is equal to A1 times e to the negative 2t plus A2 times e to the negative 50t. Now we need to solve for A1 and A2. And we do that with the initial conditions. We know from our problem that V naught is 5 volts. So we have V of 0 is equal to 5 volts, which is equal to A1 e to the negative 2 times 0 plus A2 e to the negative 50 times 0. So these values come out to be 1, and this is 1. So we have 5 is equal to A1 plus A2. So that is our first equation that we need. So that is one that we will need. So let's make, that's one we will need. And now we need to figure out our second equation. And we will do that by taking the derivative of this. We will take the derivative of this here. So dV dt dV dt is equal, that's equal to negative 2 times A1 times e to the negative 2t plus negative 50 e to the negative 50 times t. Okay. Now, let's talk about our initial equations. Remember that at time 0, let's see if I can write this. at time 0 at t is equal to 0, we have this KCL, which here the current here, and we know at time 0 this V naught is 5 volts. So we know that the current here is V naught divided by R. And we know that the current here at time 0 is I naught. And then we know the current here is equal to C dV dt at time 0. So at time 0, we have this equation, and that is equal to 0. Okay? So what we want to do is solve for dV dt. So we know V naught for our equation is 5 volts. We know R over here is 1.923 plus I naught. We know that that value at time 0 is 0. And then we have plus C, which is 10 times 10 to the negative third, times dV dt at time 0. And that is all equal to 0. So let's grab a calculator and figure this out. We want to know what dV dt is at time 0. So this is equal to 259.74, or we can just round that to 260. 260 there. And that should be negative. That should be negative, I believe. That's negative 260. Okay, so we know that this value here at time 0 is negative 260. So if we come down here and take a look at this equation here, and we put in t is equal to 0 for this equation. So we have dV dt at time 0 is equal to negative 2 a1 e to the 0 plus negative 50 e to the negative 50 times, so that's 0. So this is equal to negative 2 a1 minus 50. Oh, I forgot the a2. a2 is supposed to be here. a2. Let's correct that. My mistake. a2 e to the negative 50 t. Okay, so then we have a2 here. And we know that this is equal, this value here, because we just found that value, is equal to negative 260. So negative 260 here. And that is our second equation. That is our second equation. So what we have, if we solve here, let's solve for this. We have a2 is equal to 5 minus a1, and we'll put that into our a2 over here. And then this equation then becomes negative 260 equals negative 2a1 minus 50 times 5. So that's 250 plus 50A1. And solving that, negative 10, what's that come out to be? A1 is equal to negative 0.2083, and A2 is equal to 5.208. Okay, so our final equation, so these are important. Our final equation for the voltage via T is equal to negative 0.208 e to the negative 2t plus 5.208 e to the negative 50t. And this is our equation then for the voltage of the source-free RLC circuit that is in parallel.